Um, yep, so my name is, well, good morning all. My name is Cldwell, and I'm a PhD student at the University of Southampton. And today I'm going to talk about the deep optimization algorithm that we've been developing there in our group. And my supervisor and our group leaders are Richard Watson. And deep optimization is the idea of multiscale optimization. And we do this by inducing and searching in deep representations provided by the autoencoder or deep neural network. So first of all, I'm going to start off by introducing the deep optimization algorithm. And then we show our current results on applying the algorithm to the multidimensional knapsack problem, where we show the performance improvements in compared to other state-of-the-art algorithms. But we then take this further into trying to understand exactly how searching and inducing deep representations enable optimization to find superior solutions, and particularly the kind of problem characteristics that this method allows us to overcome in comparison to the other state-of-the-art methods. So first of all, I'm going to start off with just introducing the idea of deep optimization. So starting with a simple evolutionary process such as hill climbing, we apply this in a fitness landscape. So on the right-hand side here, have an example of a fitness landscape where the X and Y axis are the solutions and the Z axis is the quality of the solution. So if we started with a random solution in this search space and we apply the hill climbing rule, we travel up to the local optimum, and just with a hill climbing algorithm, it's very susceptible to getting trapped. Obviously, a method to overcome this is to reset or have a distribution of solutions to explore different parts of the landscape. And we can continue to do this. But in each case, we are still susceptible to getting trapped. But now we are getting trapped at a different local optimum, and we can repeatedly do this. And in doing so, this provides us with a distribution of solutions that are now locally optimal in this representation or this current search space. Of course, unless we're extremely lucky, we might find the global optimum, but as the problem size grows, this chance diminishes. But the important thing here is that the distribution of solutions provides us some information about the landscape below. And this is kind of what we develop, or where we go from next. So a way to overcome or escape these local optimum is to make large changes at this landscape level. So in doing so, we can still apply the hill climbing or the same evolutionary process. And if we're able to make large changes, we could then find better solutions still. And this is the equivalent of hill climbing in a different solution space. So we're transforming the space to a higher order organization where hill climbing can now make the large changes, or effectively this transforms the neighborhood of a solution. And in doing so, we can explore the landscape in a different way. And the idea is to hopefully find better solutions. But in this case, we require large adaptive changes. It doesn't make sense to just make random changes. We are unlikely to benefit from a large random change. And as the change required to update a solution becomes larger, the random combinations are just going to be the likelihood of making an adaptive change using random combinations just diminishes again. So what makes the large change adaptive is that it's dependent on the problem structure. And this is where we talk about inducing a high order representation to present a landscape that captures this structure to allow us to make these adaptive changes. So the idea of transforming the search space or neighborhood of solution is the idea of creating a multi-level representation of the search space. So in deep optimization, we are extracting features of variation from the data set. Oops, something's gone on. And this is presenting us with a high level of organization. So we do this by learning compressed representation of the search space and then encode these solutions to this higher space. So that solutions that originally were far away in the original representation now become closer or even neighbors at this reorganized space. But obviously at this reorganized space, we can have its own relative landscape that have features, local optimum, but we can apply the same principle of inducing a new compressed representation. And then this allows us to overcome additional, sorry, I got a bit distracted. And so this allows us to construct this deep representation of the solution space. So how this facilitates a higher order search? Well, we first start off by hill climbing in the original landscape, and then we get trapped at local optimum. And then we encode this to the next representation and explore this representation. So we can now hill climb in this space, so applying the same evolutionary process, but a higher level of organization, and then decode that back to the original space. And that's in turn seen as a large but now coordinated change at the solution representation. Again, we can continue this process by going into successively deeper representations. So if we encode to this first one, we are now trapped again. But in the new representation, we can apply the hill climbing and evolutionary process at a deeper organization. We can apply the same process, find a superior solution, and then we can decode back to see how it's changed. And it's made a large but coordinated change at the intermediate representation and made an even larger change at the original solution representation, overcoming challenges in the fitness landscape. So whilst that's the vision of deep optimization, how do we go about implementing this or emulating this? Well, the idea comes from the theory of major transitions in individuality that explains evolvability for a multiscale process. This is where unicellular life has transitioned into multicellular organisms. And this is the case where multiple individuals at one level of organization have formed relationships that resulted in a new evolutionary level unit at a high level of organization. And in doing so, individuality and the evolutionary process of variation selection is revised up to a higher order organization. And this process repeats, creating this multi-scale representation. So how do we induce this, bring this back to optimization? How do we induce this multi-level representation? Well, Richard Watson in particular has spent time linking machine learning principles with evolutionary processes. And so this is a further extraction of this, where we apply deep learning principles and linking this with the idea of extracting and representing multi-level features from a distribution of data. So the deep optimization algorithm, or our current implementation of the deep optimization algorithm, we use an autoencoder model to emulate this process of transitions in individuality. So the first step is to induce a compressed representation of the solution space. So we apply local search or just a mutation operator on each solution in a population. And this finds us locally optimal solutions at the solution level of organization, providing us with a distribution of data to then be able to learn something from. We then use the autoencoder model to induce a compressed representation of this data set. So the autoencoder model is just trained on the population of solutions that were found using local search. The model extracts and represents features of the data set at the hidden layer. And this provides us with this reorganized representation or higher order representation solution. An important aspect here is that the optimization process or evolutionary search is separated from the learning process. Learning is just rescaling the organization that the evolutionary process operates on. So after this, once our model has learned something, we then call this a transition. And now we apply the same evolutionary process, but now at the hidden representation. So each solution is taken from the population and updated by performing local search of the hidden representation. So the encoder network is used to transform the solution to the hidden representation. A local change at this hidden representation is made, and a decoder network is then used to transform this change back to the solution representation. This can then be applied through the fitness function, and selection can be applied to see if this change, this high order change, improved the solution. If so, the solution is kept, and it's kept, and the process repeats. And this is done for, and we call this process model informed variation. And this is performed for each solution in the population. In doing so, this creates a new distribution of solutions that are now locally optimal relative to this higher order representation. And therefore, the population of solutions contains information about how these higher order units now combine. So the next step is then to induce an even higher compression of the space. And we do this by adding a hidden layer to the autoencoder model. And so this is linked with layer-wise learning developed back in 2006 by Hinton, where the model is, a new hidden layer is added to the model, and now the whole model is updated using the population of solutions found by local search at the first hidden layer. And now that completes another cycle of the transition, and this can keep being repeated, constructing a deep representation of the search space, and the algorithm continues until it's found a global optimum, or no solution improvements are made at the hidden representation. So the deep optimization algorithm is within the class of algorithms that use machine learning methods to replace evolutionary operators, such as EDAs or model building optimization algorithms. The state-of-the-art methods within this class is the hierarchical Bayesian optimization algorithm and the linkage tree genetic algorithm. And they work quite differently, but in both cases, they don't use the state-of-the-art machine learning methods, which we would consider as deep learning methods. Deep optimization, its unique contribution is that its ability to explicitly transform the representation of a solution, and therefore allowing evolutionary search operators to operate in a new reorganized space. And further, it's capable of constructing a deep representation. So now we move on to exploring how this benefits the community of these types of optimization algorithms. So first of all, we started by applying this to the multidimensional knapsack problem. And we used the Turing-Beasley set that randomly generated instances, and the constraints were generated by using something called a tightness ratio, where the smaller the tightness ratio, it is considered a more complex problem or a more difficult problem. The other algorithms that we compare against use problem-specific repair operators, where they remove or add items based on the item utility. And this is using more problem structure information that's specific to the problem. Whereas deep optimization remains in a black box, treats the problem as a black box and stays within, and it deals within infeasible solutions by just only staying within the feasible region of the solution space. So no repair operator is used if a variation violates a constraint, the solution is rejected rather than being repaired. And then therefore deep optimization is using less domain-specific knowledge. Now this might seem like a handicap, but when we did this, we found that deep optimization was able to find better solutions for multiple cases in comparison to the other leading algorithms. Further, we did an experiment where we limit the autoencoder model to a single hidden layer to investigate the difference between a shallow and a deep representation. And again, we find that deep optimization is capable of finding superior solutions when it's allowed to use a deep representation, suggesting that the problem structure that deep optimization is being able to extract is actually deep, as well as outperforming the other state-of-the-art methods. So that was all well and good, but we really wanted to understand why and what types of problem characteristics is deep optimization, being able to extract. So as we said before, even when alternative methods use extra domain knowledge for their repairs, deep optimization is able to find better solutions. And the results indicate this is deep. These randomly generated instances have unclear problem structure. We don't really know what deep optimization is able to exploit that these other algorithms cannot. And further, how a deep representation is allowing us to exploit information that a shallow representation cannot. So the differences between these methods, all algorithms are trying to reach the same goal. They're using the model to compress the search space and then searching within this compressed representation to find fit solutions. But there are subtle differences. And the first one is the model capacity. So the hierarchical Bayesian optimization algorithm uses a Bayesian network. The linkage tree genetic algorithm just uses a tree representation. And deep optimization uses a deep feed-forward neural network. So there's subtle differences there. The next difference is how the model is being used to inform search. So how it's searching in this compressed representation. And the best way to explain this is by example. So if we had a distribution of promising solutions and observed that two particular solution variables took the same value, such as 0, 0 and 1, 1 in a binary case, model-informed generation, this is when the model generates 0, 0 and 1, 1 more often than the alternative combinations. And this is what HBA, or hierarchical Bayesian optimization algorithm, does. There's model-informed crossover, and this is where the model just represents the linkage information. So that is that this variable and that variable share a linkage, but the value of the variables is taken from the population and to perform crossover. And this is what LGGA does. Model-informed variation, this is when the model represents 0, 0 and 1, 1 as neighbors in a higher or hidden representation in case of deep optimization, but in a higher order space. And this is what deep optimization does. So to evaluate these differences, we constructed a synthetic optimization problem that separated the way the structure needs to be represented, allowing us to investigate the model capacities, and the way the structure is used, allowing us to investigate the differences between model-informed search. In doing so, we've created 3 different characteristics of structure representation, which was non-overlapping case, which is our baseline, and overlapping and non-pairwise relationships between the solution variables. We then did 3 different characteristics of the way to use the structure, and this was generating combinations, hierarchically generating combinations, and rescaling search. And this gave us a total of 9 combinations to explore. At this stage, we have only started really exploring and trying to understand the differences in the problem structure. And here today, we're showing our results so far, but this is by no means this is the only structure or a extensive review. This is still much more to be explored. So in all cases, the headline is that deep optimization is the only algorithm to scale polynomially in all cases. So I should have said before, the experiments we were performing is just a scaling analysis. So the time required to find a global optimum solution, and we measured that. And as the problem size grows, we measure how the scaling of the algorithms perform. So we find that, to conclude that, we find that the linkage tree genetic algorithm fails as the size of the overlap increases. So this distinguishes the induction capabilities, or well, the induction limitation of the linkage tree genetic algorithm in comparison to HBA and deep optimization. LTGA and HBA fail to explore the neighborhood of organization, distinguishing the model-informed variation capability that deep optimization uses. HBA and LTGA fail when there's with non-pairwise relationships, distinguishing the induction capability of deep optimization algorithm. And the deep optimization limited to a single hidden layer fails in the case of overlap and non-pairwise relationships, distinguishing deep representations from shallow representations. So to conclude, that deep optimization showed an impressive performance on the random knapsack instances. And we then found that there does exist distinct problem characteristics that deep optimization can solve that other state-of-the-art algorithms cannot solve. Further, there does exist problem structure that a deep representation is required for that a shallow representation cannot solve. Of course, there's so much more to understand about the problem characteristics, whether there exists other problem characteristics we haven't found, but then also the abundance of these characteristics in the knapsack problems. Was this really the reason for why we saw differences in knapsacks? We don't have that information yet. But the idea is that rescaling simple or limited optimization capabilities to higher orders of organization can enhance these methods. And this demonstrates the intuitive links between evolutionary transitions and individuality and deep learning for evolutionary algorithms. And of course, strong motivation for further investigation. Thank you very much for listening for my talk.
That was extremely interesting. We already have some questions. One that was deemed obsolete by the author, but actually I would ask it anyway, because the original question was, are we talking about discrete problem or continuous problems? And then as you presented, said, okay, the previous question is obsolete. It was an empty knapsack. But in theory, if I understood correctly, this technique could also be applied to continuous problems.
Yeah, so most of our studies has been limited to discrete problems, but we have done some exploration on continuous problems, and we did see the same kind of performance and being able to make large changes. So it is definitely, we don't see there being a reason it can't be applied to continuous problems. It's just it hasn't been thoroughly investigated.
But an autoencoder can be applied in principle to any kind of.
Exactly, yeah.
Then we have another question that was in slide 18. You portray time needed to find the global optimum, but how do you know what the global optimum value is?
So an important thing of our synthetic problem construction is that the global optimum is calculable in polynomial time. So we do know exactly what the global optimum solution is. So unfortunately, there's not enough time to kind of describe how we create those synthetic problems, but it is based on, we know it basically.
All right. And then we have a question from Emma. You can unmute yourself.
Hi, can you hear me?
Yep.
Yes, yeah.
Yeah, so it's a comment rather than a question, actually. Very nice talk. I think it's really interesting work. I just wondered whether you'd come across Adam Geyer's work. So actually, he works in continuous optimization in design problems, but they're doing a very similar thing where they train an autoencoder and then search in the latent space. But the comment I wanted to make was that what they observe is that because you're training the autoencoder with data that you're generating from your search base, it's a very exploitative algorithm because you're essentially biasing you're biased by the training data.
Yes, yeah.
So what they do is they add an additional phase where they mix that with a very explorative part. So there's an explorative kind of loop that searches in the kind of unknown bits of the search space, which is mixed with this learning in the latent space. And they show that they get a better result by mixing the two things together by having this explorative phase as well. So it's just a comment to have a look at.
Excellent. Yes, I wasn't aware of that. What was the name?
I'll put it in the chat.
Thank you. That'd be brilliant.
They work in automated design of objects, but I'll put the information in the chat.
Thank you very much. That'd be brilliant.
And we have another participant that is says I have about 62 more questions. If there is time left, I'd like to do one or two. That is okay, but I would first take the one from Ole. So you can unmute yourself.
Yes, hi there. Thank you for an interesting presentation. I was wondering, have you looked at image processing and the searching in a higher, high resolution versus low resolution? That seems quite natural to me. I actually started thinking about that when I heard your presentation. And since you're working with an autoencoder, that also seems quite natural to do.
Yeah, it's something we have thought about as well, and I think that would be really impressive to see. Certainly, is in presenting the idea to people. I think it, like you say, is quite natural. It's just not something we've explored at the moment.
Yeah, I haven't thought about that before, but when I saw a presentation, that sort of clicked with me, because we've had better results when working with low resolution images compared to high resolution. But of course, I'm suspecting it all depends, on what type of image you're looking at and so forth.
Yeah, no, I think it's a really interesting idea. It's I sometimes refer back to image processing when trying to describe the idea of, like say at different resolutions to explore. So
yeah, great. Okay, thank you very much. In any case, thanks for the nice presentation.
And I don't know, maybe Dan Vanderberg wants to unmute and ask some of the questions he has.
Yes, please. Jamie, this is very interesting stuff that you presented today, and I have a lot of questions and a lot of ideas. Let me first say that about these continuous problems, that I really think that the playing field is a lot different. Because, and this is very recent, we've done some research on a kind of a local global search algorithm made at London and Essex, and we've actually presented it in this conference in the LBAs. And for many continuous problems, we seem to be able to find, for about 50% of these problems, we seem to be able to find the global minimum. This without machine learning, it's just it's in the LBAs. Check it out if you'd like to see it. But we think it has to do with the folding, and I cannot express this differently, and I only understand it a little bit, but the folding of the continuous functions as they stack up in higher dimensions, that the sigma, it kind of folds the function back to itself, by which it becomes more easily explorable. From that, I would like to skip to the plenary lecture, also in this conference, by Daryl Whitley. And what he said was very interesting. He was talking about work by Gabriela Ochoa and work by himself. And it was about genetic algorithms able to find local and global minima. And what he said basically was that local minima are connected through each other via a good crossover operator. Now, this kind of suggests that this crossover operator combines certain structural properties of these local minima to a global minimum. He showed some work, I think, on traveling salesman problem instances. Mm-hmm. So that might be another part where your research is very closely touching his. Mm-hmm. And one thing that has been skipped completely, but it's old work, is the work on backbones of, I don't know if you're familiar with this. Like these problems that all of which all good solutions have a lot in common, or somewhat in common, or there's different kind of backbones. I'll just come to one question, which I think is a very prickly point and very vexing in this in your investigation. Is you're talking about the multidimensional knapsack problem and finding the optimum. How does, and this is very difficult, if you have no idea of just suggestions, it's fine. How does the generation of instances, like how you make these problem instances, affect the structure, if you like? It's a very, do you understand my question? It's very global.
Yeah. I think, and this is the reason we wanted to explore our own synthetic problems, because we know the structure, so we can see, is our algorithm exploiting the same, what we expect to see? So looking at the neural network, trying to understand it from this way. In the random generating of these problems, I mean, my intuition is that the structure there is just going to be so almost noisy. It's going to be really hard to use this idea of that local optimum are leading to this kind of global optimum structure. So I think in these cases, on my synthetic optimization problem, we can find a global optimum because we know the structure. And these synthetic cases, it may not be this kind of assumption about using local optimum to give us information to change our crossover operators or the way we search. that assumption just might not be valid in these random instances. But we can still make great progress in moving towards better solutions. But that one global optimum point just might be a bit of noise or random. There's almost like no reason for it, I guess. So I think that's the problem on generating random instances, is that what are we really trying to show here? Is it the assumption that identifying and exploiting problem structure leads us to better things, or are you just trying to show that your algorithm can scale, better than somebody else's? So I think that's a really good point. But I guess I've only got an intuition on it at the moment, rather than anything else.
I have Alberto, if you allow me, I have one follow-up on this.
Wait a second. I will ask a question, because another question came up in the chat, and then I will let you ask the follow-up. So Sebastian Varel is asking, did you compare to efficient local search like Taboo and so on, that are very efficient on MKP, but they use the knowledge of the problem?
No, is the simple answer. And the reason was just wanting to stay. We wanted to show algorithms that are trying to induce the problem structure from the instances. There will be better algorithms on these knapsack problems that are more specific, using more, been developed much longer than ours. So the knapsack problems that we applied it to are actually not very large problems. We were just exploring the types of problem structure that deep optimization could potentially exploit in comparison to others on a problem that's not synthetic. It'd be interesting to people. And this is what, going back to that kind of random instances, is like, can we really expect to induce meaningful structure when it's been randomly generated? So that may be a counter argument, but no, I think that those algorithms are likely to outperform, deep optimization.
Okay, thanks. And now I will let Dan ask the follow-up question here. Yeah,
okay. I'm going to drop another bomb, just for mutual interest, of course. So there's this movement underway. It's a consortium of like 13 or 14 different writers, and it started off at Gecko. It's led by Thomas Bartz-Beilstein, and it's about proper benchmarking. So using what kind of sets do you use to challenge your algorithms? And I have a kind of a lone position. I have the feeling I have a kind of a lone position in that group, in that I really want to address the issue of using random instances to test functions. And the reason for this is that we have two recent investigations on the Hamiltonian cycle problem, which is also a discrete problem, but it is a decision problem, slightly different. And it shows that very, very large random instances, random collections of problem instances, of course, they contain hard problems, and we know where they are. That contain a lot of time. But once we start evolving these problems themselves with evolutionary algorithms, very far away from this hard core, there are much, much harder problems to be found. And where it links up to your investigation, in my view, in the future, is that these problems are suggestively non-random. Mm. So the hardest problem instances might actually be structured and be non-random. You are looking for structure, so that in the future these two might come together somewhere. Yeah, if you have any ideas on it, please shoot, because I'm fascinated.
We are constantly looking for, like, say, those problems with that structure. And when we look at the benchmarkings, it's always been random instances or just unknown structure. So we've struggled for that and kind of had to turn to creating something ourselves. So that's fascinating to hear that that's kind of the way you're thinking as well. So it'd be great to talk to you afterwards.
I'll be here. Thank you.
Cool.
All right. There are actually, Emma posted the information about the other researcher she was talking about in the chat. And Sebastian had a follow-up that says, so maybe black box problems would be better as benchmarks.
Yeah, so we were treating them as black box problems, but it's we still want to be able to evaluate the performance of this algorithm, at least initially. We still want to understand the structure. So it's almost like we know the structure and therefore what it's looking for, but we treat the algorithm is treating it as a black box problem. It's just allowing us to evaluate what did it exploit the structure we expected and stuff.
Yes, in this step of your work, it's important to understand whether the algorithm is actually able to exploit the structure, and it's easier to do when you know there's a structure than it's perfect